All right, folks, welcome again to our paper reading. Today's topic is a very interesting paper that just came out a couple of weeks ago. It's named AlphaGeometry, an Olympiad level AI system for geometry. This is an emerging trend recently. For the longest time, we believed that machine learning models, even large language models, and for example, OpenAI, ChatGPT, or Anthropic's Cloud or Bard, they learn from vast amounts of data. And even though they are generative models, what they generate is essentially some form of interpolation from the knowledge they have. They are either regurgitating the knowledge, or they are interpolating and generating new stuffs from that. I myself used to believe that, but recently we are seeing that you can actually use these AI systems to make fundamentally new discoveries. 2 weeks ago, we covered fund search, where we showed that, for example, to bin packing, it came up with a method far superior to what the best heuristics have come out with. This week, or today, we're going to do another paper that came out of DeepMind, AlphaGeometry. What it claims and shows that it can do is reach Olympiad gold medalist level performance in proving or solving problems. Now, those of you who are, almost all of you know that Olympiad math is international math. Olympiad is a pretty arduous test. One has to prepare for it for a long, long time to even compete and then reach to the level to participate in it. The winners are really exceptional. To say that we have a computer system now, we have an artificial intelligence now that can achieve comparable levels of performance in proving theorems is to make a fairly astounding statement. It's a remarkable thing that it can do it. Not only can it do it, it can do it within the same time limit given to the Olympiad competitors, within the same time box. So that is quite remarkable. It is, however, a very focused system. It can do only geometry and a very specific form of geometry problems, the kinds that you tend to see in the Olympiad, Euclidean geometry. So imagine triangles and circles and so forth on a page, right? And proving theorems about that. So while it is narrow, it's sort of, I suppose it's a harbinger of things to come. It shows where things are going forward in 2024. You see that we can use LLMs, large language models, and these neural architectures to actually make, to actually do the sort of things we thought these machines could not do. For the longest time, we believed that large language models are rather poor at reasoning. That statement, interestingly, hasn't changed. Yes, they're getting better, but they're still poor at reasoning. But what you can do is you can couple it up with a strong deduction engine, a strong reasoning engine, and have an interplay between a large language model, which is generative, which can come up with creative suggestions, and a deduction engine, which can rigorously check out the correctness of those statements. And this interplay between a deduction engine, and in some sense you can think of it as a generative or a creative engine, is AlphaGeometry. That's a core idea that we'll talk about. So with that basic sort of a summary of the thing, I would like to now start walking through the paper in a little greater detail. I'll first go through the blog, which is a lot easier to understand. And after that, I'll walk through the paper, both of which I think are very well written. So As usual, I'll be writing on top of the paper itself and highlighting things here. Is my screen visible? Am I sharing my screen?
Yes, you are. Yeah.
Okay. So it starts with a very broad statement. It says, reflecting the Olympic spirit of ancient Greece, the International Mathematical Olympiad is a modern-day arena for the world's brightest high school mathematicians. The competition not only showcases young talent, but has emerged as a testing ground for advanced AI systems in math and reasoning. In a paper published in Nature, we introduce AlphaGeometry, an AI system that solves complex geometry problems at a level approaching a human Olympiad gold medalist, a breakthrough in AI performance. In a benchmarking test of 30 Olympiad geometry problems, AlphaGeometry solved 25 within the standard Olympiad time limit. For comparison, the previous state-of-the-art system solved 10. So as you can imagine, this is quite a jump from what was the state of the art in AI systems, ability to solve this kind of problems. Now, observe interestingly that the gold medalist solves 25.9 problems, right? So it doesn't quite catch up to the gold medalist. But it's remarkable that in the very first version of this approach, it has come within touching distance of the gold medalist. That's sort of the main thing. And then I won't go over this blog line by line, but sufficient to show this graph. It shows the previous state of the art was 10. The bronze medalist was 19.3, silver 22.9. So as you can see, it is better than the second best, right? But not yet beaten the best. That obviously opens the door for further good work. Now,
the question.
Yeah, go ahead.
There's a time limit to the Olympiad. Here, the AlphaGeometry probably did it much earlier than.
No, it did it in exactly the same time.
Same time, and
yes, also. Right. So the approach that it takes, and so folks, those of you, I mean, not everybody may be familiar with terms like neurosymbolic systems, and I'll try to sort of explain, but this paragraph is crucial, so I'd like to read it. AlphaGeometry adopts a neurosymbolic approach. AlphaGeometry is a neurosymbolic system made up of a neural language model and a symbolic deduction engine. May I elaborate on this a little bit? It's made up of two pieces, a neural language model. So neural language model, just think of your large language model these days, right? Of which ChatGPT has become or Bard has become the poster child, or Cloud, or whatever your favorite engine is, sort of the poster child. And a symbolic deduction engine. So symbolic deduction engines, if you're not familiar with, these are a development in computer science. What people have done is these engines have been evolving, believe it or not, since the 1950s, ever since the first computers came out. People have been trying to use these computers to prove theorems, deductions, right? To deduce, to prove. And to do that, you have to represent the problem in a symbolic form. Let's say A and B. If it is an algebra, it's very easy, right? If you say X is 20 and Y is 30, prove that X plus Y is greater than 40 or something like that. Right? So those are symbolic deduction engines. Now, as you can imagine, symbolic deduction engines are deterministic. If they say something is proven, it's proven. Right? The problem with deduction engines are that they are not creative. Right? If it cannot think like human beings. If for a moment you think any geometry problem, and in the below, they give a particular geometry problem, which is very illustrative, you will see in a way, the missing link from symbolic deduction engines, why they could not achieve Olympiad level mathematical ability, or they could not prove theorems except some of them, a small set. They were given some sort of a so-called human demonstration. If you see a problem like this, take this approach, things like that, right? In which case, a sort of bit of hardwiring, a bit of experience, and they made some progress. But this paper takes a different approach. So hopefully that explains the first line. AlphaGeometry is a neurosymbolic system made up of a neural language model and a symbolic deduction engine, which work together to find proofs for complex geometry problems. And I find this statement to be the heart of it, or heart of the approach. It goes on to say, akin to the idea of thinking fast and slow, Thinking Fast and Slow, folks, is a very popular book. The author of that book received a Nobel Prize for discovering those ideas. What it says is that the human cognitive system has two parts. One is that just makes quick, intuitive, creative leaps and jumps to conclusions. And the other is a very slow, deductive reasoning, but it doesn't make any intuitive or creative leaps at all. It slowly deduces it. And to illustrate this point, I suppose it needs explaining for folks unfamiliar with the book, is this idea. I hope I don't get it too wrong. I'm just speaking from memory. One example it gives early on is, if you're asked in a given area, farmland, like say middle of somewhere, right? You find a person, let's say Alice. She is quiet, likes solitude, reads a lot of books, and so forth. Now here's a question, is she more likely to be a farmer or a librarian? Would anybody like to venture a guess who has not read the book? Go ahead. A librarian. Right? Anybody would like to disagree, but you have to have not read the book. So that is thinking fast. That's making intuitive leap. But now I'll give you a slower reasoning. Most in an agricultural area, most people are farmers. Right? And human beings come in diverse shapes and sizes. Even amongst farmers are people who like solitude and people who like to read. In a town, there are not that many librarians, just one or two librarians, few librarians. And now, when you put those things together, is it far more likely that Alice is a solitude-loving, book-loving farmer, or is she a librarian? Put that way, you realize that this is, obviously, if you work it out as a probability, you'll realize that it is far more likely that she's a farmer. And that is slow deductive reasoning. So that is thinking fast and slow. And I apologize if I have butchered that example. One of you can, who recollect the exact, please feel free to correct me on that. But with that idea, what these folks say, that akin to the idea of thinking fast and slow, one system provides fast, intuitive idea, and the other more deliberate, rational decision making. So the intuitive ideas, so-called intuitive ideas, is coming from which of the two you would imagine, from the large language model or from the deductive engine? It should be the large language model. In fact, what we may consider their ability to hallucinate is actually their creativity in some sense, right? And the symbolic engine is, of course, will take its time and make slow, deliberate, logical steps to come to conclusions. Because large language models excel at identifying general patterns and relationships of data, They can quickly predict potentially useful constructs, but often lack the ability to reason rigorously or explain their decision. So this speaks to the fact that large language models are not very good at deductive reasoning. It's a fact today, circa February 2024. Symbolic deduction engines, on the other hand, are based on formal logic and use clear rules to arrive at conclusions. They are rational and explainable, but they can be slow and inflexible, especially when dealing with large, complex problems of their own. Thus, AlphaGeometry's language model guides its symbolic deduction engine towards likely solutions to geometry problems. Olympiad geometry problems are based on, etc., etc. So it goes on, and I wouldn't go on, but let me just explain how this engine works. So the very simple example that they give, I'll just sort of zoom it in here. See, folks, you see, and this is the core of the idea, beautifully said. Suppose you have a triangle. In this triangle, you're given the fact that, oh, sorry, why is this still, yeah, this side is the same as this side. AB is the same as AC, right? These two sides of the triangle are the same. You have to prove that this angle is the same as this angle. Proof ABC, these two are the same as BCA. How do you prove it? Now, a little bit of a fact. To prove such things, whenever you get proof, what you need to do quite often, and we do it intuitively through practice, through learning geometry, we tend to stare at the problem and say, we know that you need to show similar triangles, something is similar to this, or some other means of that. But in doing that, you add something to the figure, right? Those are called auxiliary constructions. This paper uses the word auxiliary constructions. And if you think about it, that if you were to put this, okay, from here, take this point B, which is what it does here. So actually, because it does here, I'll just point to that. Please observe, the moment you do this auxiliary construction, put a point D, and you draw the line from A to D, D being the midpoint between, D is the midpoint, this is the same as this, you realize that after that, the proof becomes very easy, because if this is the same as this, if this is the same as this, and of course this is common, the two triangles are identical, isn't it? And if they are identical, then of course these two angles have to be equal. So this particular proof needed you to make the creative leap of putting this line A to D, putting a point D and putting a line, a midpoint D. This is your creative or your auxiliary construction. Once you have put this, then you can have your deductive engine go at it and prove it. Right? So what is the system? What is the AlphaGeometry system they have cooked up? What they say is that given a problem, first of all, just give it to the deductive engine and ask, can you prove it? So a deductive engine will look at this triangle and it will try its very best to come up with all sorts of statements. But the one statement it may not be able to come up with is that these two angles are equal. Right? A deductive engine is supposed to deduce every single thing it can deduce from the data it has. Right? So from the data here, the data that is here, it may make some deductions, but it may not be able to deduce or won't be able to deduce that these two angles are equal. Once it has exhausted all that it can deduce, you then go to a large language model and you say, come up with a new construction, new thing, a new, right? And so it will say, all right, construct a midpoint between B and C. Let's add a point D. The moment you add a point D, and by the way, it may come up with many other constructions which may not work, right? So it isn't that LLMs are magical. They would know exactly which path to take. It may take many, many paths that may not work. But if you have trained the LLM well, then hopefully it will pick a reasonably good path, right? So it picks this, and then the deductive engine again goes and says, now that you have one extra bit of information, what are all the things that you can deduce? So certainly it will be more than what it could deduce before, right? And this time around, it will be able to deduce with just this one new construction, right? And it will come up with this kind of a deduction, which is exactly what we talked about, right? Therefore, proving the theorem. But if it could not, then you go back to the language engine and you ask for one more new construction. And you keep on asking for constructions and you keep using the deductive engine. And so it is an interplay between the LLM and the deduction engine. But that brings up a very interesting problem. I don't know if this blog talks about, but we'll get into that in a moment. The problem is, and it has been an outstanding problem in solving theorems using a deductive engine for a very, very long time, it is that people have known that to solve geometry problems, you need to do auxiliary constructions like this. That's what humans do. But humans intuitively know through practice what auxiliary constructions to insert. They don't look at random constructions. How many constructions can you do? You could do all sorts of constructions. You could have said, okay, why don't you go here and put a point here? Why don't you go here and put a point here? I mean, you could do all sorts of weird constructions. The number of constructions, auxiliary constructions possible is practically infinite, right? And because it's infinite, you cannot say, hey, just come up with a random auxiliary construction and solve the problem. Give it to the deductive engine to solve it. Right? That wouldn't work. And therein is the main magic of this paper. This paper, the point is, how do you train a large language model? Not to come up with random auxiliary constructions, but to come up constructions that are within a very narrow range, which are very likely to be the good construction. Sometimes are wrong, sometimes are right, but suppose you ask it for 10 constructions, 10 good possibilities. So that's a beam search. Within the entire space of possible constructions, you do a beam search and you pick up 10 constructions. Those are pretty good constructions. So that, the deductive engine has to just work with 10 new auxiliary pieces of data, and it can then go and parallel process, do its deduction along all of those different constructions and see if it is moving the needle forward, right? So that is one of the things that this paper discusses. Now, to illustrate, it shows an example. This is an International Math Olympiad problem. It is so complicated that it takes a whole paragraph to write it. And basically, I'm not going to go into what it is, but if you look at this thing, and if you remember taking courses in geometry, you would agree that for normal Joes like you and me, seeing a question like this is exactly when we would say, okay, let's skip this question and move to the next one. Right? It looks way, way too hard. And obviously, that's the nature of the Olympiad question. AlphaGeometry did manage to solve this using its various construction loops. And actually, when it did it, it turns out that to prove this theorem, it did only 3 new auxiliary constructions. One is it constructed D as a midpoint between B and H, something that would not have occurred, obviously, to me at least, because it says that, see, you see B and H here? Put D here. This is your D. Put a D here. Then it does another auxiliary construction, G. It's a midpoint between H and C. So where is H? In this big figure, somewhere is H. C is here, and H is here. So in this point, it makes a midpoint construction G here, right? And then it says construct E as a midpoint between M and K. Now, where in the world is M? M is, well, here. So M and K. So it is saying, put a midpoint here. And if you find these three auxiliary constructions, it turns out that this nightmarishly complicated geometry problem can be solved after that. You can prove it, right? Which it does. And how it does it, we'll sort of go through that. And so what
Sorry, just as a quick question, I have done a few of these problems before when I was in high school, so it's been quite a long time. But from what I remember, this is actually how you are supposed to solve this kind of problem. So when it proposes like the new auxiliary constructions, is it being fine-tuned on like the existing proofs that exist? Is that kind of how it like starts its search, or is it just kind of doing it creatively?
Oh, this question couldn't be more apropos, and thank you for asking that. Beautifully, it does not actually rely on a database of existing proofs or what are called human demonstrations. The most interesting or the most clever thing about this paper is it doesn't go back to our database of proofs that exist. To your point, yes, we are all taught in geometry to add these auxiliary constructions to prove theorems. So the thing is, we as human beings we get pretty smart at finding the right points or doing the right things through practice. Machines have never been able to do that because there are infinitely many of them. And the beauty of this new breakthrough is that it says there is a proper way to go find these auxiliary points, almost like human beings do. The good auxiliary, strategically good auxiliary constructions that just like human beings do. Now, to the second part, if it cannot use historic data of proofs, then how does it do it? It turns out they use a very clever trick, and we'll get to it. That's a little bit of the detail. What they do is they generate their own database of 100 million synthetic data examples. So the way they do that is quite interesting, and we'll get that's sort of the technical part. We'll get to it, but they create their journeys. They create their own theorems and proofs, literally. So they will just take a triangle, right? Put something somewhere, do an auxiliary construction somewhere, and then it will lead to the symbolic engine will end up proving something, right? And then what do they have now? They have an auxiliary construction and they have a proof, isn't it? A way to prove it. That becomes their data. And they keep repeating this process over and over and over again so that they have millions of data points to train a large language model on, or a transformer on, in which they say, hey, if this is your problem and this is what you have to prove, here are some good auxiliary constructions. Here are some good premises to pick from.
So this is kind of a follow-up question to this, but I also know that in game theory, there's this idea of finding symmetries across multiple different subgames so that you can apply the same like strategy to like different games. Is it then able to take like multiple examples and simplify it down to like one general answer, or is it that like it can only be general up until a certain point, otherwise it doesn't recognize it anymore?
Actually, I do realize what you said. In this particular paper, they actually don't talk about generalization from what it has learned. Having said that, to the extent that you're training the transformer with hundreds of millions of examples, you're giving it in starting points and end points and telling what constructions to use, implicitly it's learning those generalization rules. But it's not learning it through symmetries. In fact, one of the details that I didn't intend to cover is that the proofs that it comes out with are quite asymmetric. Human beings tend to when we prove theorems, we tend to exploit symmetry a lot. What we find here, what these researchers found in this paper, is that the proofs actually look quite asymmetric. They don't exploit symmetry much at all, right? And you can almost consider it as a way forward or scope for further work. What if we could teach it to exploit symmetries? Would it do its proofs even better? Perhaps. So, does that answer your question?
So, if I understand, essentially they simulated or generated the data, right?
Yes. Yes.
Then what to backwards to create the constructs.
That is right.
Yeah.
So you basically do this. You take, like, for example, they show the process here, but you can imagine that you take a triangle, right? You teach it that if you drop this thing here, right? What can you prove? You can, for example, you know that this is equal to this, right? Now, suppose I tell you that this angle should now be, because this is shorter than this part, for whatever reason, because this angle A is greater than B. If A is greater than B, then maybe you can show that this length is shorter than this other length. Hey, you now just got a result, isn't it? And so you got, with this auxiliary construction, you managed to prove a result, right? And so you create millions and millions of these, hundreds of millions of these, and that becomes, and it may almost look, to human beings, it looks obvious, all right? But hey, that's training data. And it turns out that if you train it with this simple data, and it goes into the details of all of that. And the most impressive thing is that, see, with geometry has been very hard to represent in symbolic form, right? Algebra is easy to do. That's why algebraic solvers are much more prevalent and powerful. But geometry has been harder to encode, and data, to create training data for it, has been rather hard. So one of the clever things that made this discovery possible is they came up with a system to create this data, right? And with this data, then they went back and trained it over and over again, right? And it's all from the interplay between a solver, a deduction engine, and a LLM. So that's what this is. Now let's go to the actual paper. Now this paper came out in Nature. As you know, Nature in the STEM field is perhaps the most prestigious journal, right? Most of us aspire to get one paper into Nature in our lifetimes, right? If we are very, very lucky, if we make some significant breakthrough. So obviously, when something shows up in Nature, it speaks to that. It's a vote of confidence on how non-trivial the result is. So I won't go into that, but
so this is fairly old in the sense that it was submitted in April 23. So maybe the field has even gone further ahead now. Right?
Yes, it is. I'm sure that they have advanced, but they haven't revealed anything so far. Perhaps time to reach out to the researchers. Right. So this is the thing. How do you generate it? There is a crucial diagram. So this part is obvious, guys. We went through this, right? You have something like this. A solver cannot deduce, a deduction engine cannot yet prove the theorem, right? It may deduce all sorts of things, but it may not be, it is not able to solve. At that moment, you go to the language model, a transformer, and you say, hey, you are a generative engine, generate a new construct, a new premise. It will do that, and then you give it to the symbolic deduction engine again. Either you are in a solved state or you haven't solved, and then you go back to the language model and ask for another new construct, right? And so you keep going on in a loop, right? Back and forth between the LLM and the deduction engine. Right? And that is it. Now, this is the heart of how it goes, how the new data is created. I believe one of you asked, where's the data coming from? So if you look at this thing, and I'll read the figure 3, I'll read the bottom first. and I think this is perhaps the most important figure here. We first sample a large set of random theorem premises. So here we go. You look at this picture, and from this, you can come up with a set of premises. Premises is, I see that E, A, D, H are cyclic. Like E, let's say E, A, D, H are cyclic. You would agree that they are cyclic. They form, what is it, a trapezoid? Right? They are cyclic. And right? These things. Now you can say that, see, where do these sort of premises come from? This part, I think, requires, and the way this paper is written, you have to actually jump to the very end to see what is going on. In fact, beyond the end to the appendix. Where is it? Oh, good grief. It is article. Here it is. Actually, there are about 50 odd things that it says. What it says is that these are your auxiliary constructions. Right. You notice that even though you can have infinitely many things that you can come up with, you limit yourself to a very finite vocabulary or set of possible constructions. It just says that sample from this table. Sample. Just sample, pick something from here. Right? So when you do pick something from here, then you can have, right? You can apply your algebraic reasoning, your proving, and you can end up by picking something here. You can come up with all this. Let's go back, and so this actually is Nature Papers' interesting way of putting the paper. It gives you the core results, but the method seems to have, or some of the details are way back there in the appendix. But what happens is that from some construction that you do, you can come up with intermediate results. Right? So, for example, it says we can deduce that the fact that this is a cycle means that we can prove EAH, that is this angle, is equal to EDH. Let's say E, where in the world is D? EDH, this angle. Right? You can prove that. Why can you prove that? Because they have the same base, right? And they have, okay, let's assume that they can prove. It will take me a while to prove anything like this. So let's say that you can prove this. And from this, you can go to this statement. There are other paths to go from here. Like, for example, you can prove EC is perpendicular to EA. Where is EC? EC is perpendicular to EA, which is why? Just by construction, I suppose, or something like that. At the end of it, you come up with a result. Like these results, let's say, lead to this result. And you're just playing with a triangle. You're not yet given a job, right? You're given this figure and you come up with a result. Let's say that you consider one result interesting, right? One deduction interesting. What you do is, now you have data. What do you have? You have a list of, look at this. This is from this, you can work back a graph, right? A directed acyclic graph. You can look at it forward or backward. I forget which way it looks at it. You can say, to prove this, you need to prove, like you can prove this by going along from here, along this path. You need to prove this, right? So you can have a set of premises. You can have something to prove, the node to prove. Let's say that this is the node that is the thing to prove. And then you have a graph associated with, right? Given a set of premises, you can build and give the node, and then premises, conclusion, and proof. Because the graph is the proof. Would you agree, guys? Right? The proof is nothing but a set of subproofs. each of which the deduction engine says is correct. Right? And the fact that you can do this, lots of these become your training data. And this is the clever trick they use to generate vast amounts of high quality training data. Right? And as you can imagine, it doesn't just prove this. You can come up with all these other grayed out things, and they will have their own sort of, they will lead to their own data generation, their own combinations of premises, thing to prove, and the graph of deductions that will help prove them. Right? So this is that. And what they found is, and this is a part I suppose we can talk about, what they found is that, and this part is interesting actually, that a trivial theorem, proof length, like for example, to prove proof length is equal to 1, something like that, to prove that this is perpendicular to this. How many steps does it take to prove this? It turns out that something like this, you prove with just one premise or one premises, auxiliary construction is enough and you're done, right? To prove something that requires a lot of steps, a lot of auxiliary constructions, and sometimes an impressive 240 constructions, right? Here is a theorem that it proved in 247 steps. Means it created 247 sub-steps or intermediate things along the way to get to it, right? And so if you look at the frequency of it, it is on the logarithmic scale, log scale. The first thing to notice is it's on a log scale. What do you notice? That the vast majority of things are proved in length, fairly small length, a small number of auxiliary steps, right? Which is what it is. Like you don't. Most of us find it extraordinarily hard if we had to prove a theorem in such huge number of steps. I mean, those become in mathematics, as you know, those become entire multi-year projects for groups of mathematicians. They make it a project to solve very, very hard theorems. Now, take, for example, Fermat's last theorem or something like that. Well, this is geometry. Now, look at the results, and I think we are coming to the close of the time. These results are quite impressive, actually. I find them to be very interesting. So if you use just computer algebra, you realize that it solves about, and it is the state of the art. It could solve about 10 of the Olympiad problems. I believe the total is about 30 or something like that, 10 of them. Yeah, out of 30. Right here it says, out of 30. 10, think about it, guys. State of the art was 10 before this paper. Then there GPT with the whole might of GPT-4 managed to solve exactly 0 of the Olympiad problems. Right? Because those things are not reasoning engines. The core idea is that you need to couple it up with a deduction engine. Now, there is more happening here. And I'll talk a little bit about what they found, because there's some subtlety to what they found. So obviously you notice that you can use, one of the things they did is they also use algebraic reasoning. They created a system of algebraic reasoning into the whole thing. The number goes up, some other things. And then human designed heuristics. So what happens is, if you take the best of heuristics that people have created and how to go about solving problem, you reach a number like 18, right? With a deductive engine. So the lesson here is, if you just use a deductive engine, you can get to 18. If you just use a LLM, you'll be squatting at 0 when it comes to Olympiad level problems. But when you put it together, you get to 25, which is quite impressive, considering that the gold medalist is at 25.9, just one more problem ahead, right? But observe something interesting. They show that if you don't do pre-training of the model, if you just take this core idea, take a language model, have it suggest auxiliaries, but do a beam search, like limit it to k is equal to 10 or 20, and then go about it. It already achieves quite easily 21. If you think of 21, this beats the current state of the art right there. So you right off the bat, you know that the idea is right. Let's put a language model together with a deduction engine. And then good things begin to happen. So you can see that quite easily they reach 21, right? And when you do some, you don't do any fine tuning, but let's say that you do pre-training, but you don't do fine tuning. So 23 represents that you did do pre-training with those 100 million examples. What do you end up with? Right? You make some progress with fine tuning and everything. You get to, so the best result is 25. And the impressive thing here is that going from 23 to 25 actually, with all the fine tuning with millions and millions of example, took you 2 problems ahead. Now 2 might not look impressive, but those of you who know how these Olympiad systems work, remember, whereas without fine tuning, you are at, look at this, it's about 23. You are a silver medal winner in the Olympiad, 22.9, right? Whereas with the whole system in place, you do extremely well, right? But it seems, so now here's the thing, going past 25 must be hard. They came within touching distance of the gold medal. 25.9 was where the gold medalist was. With the fact that they published this paper when they did, at some point they must have said, okay, we are hitting a wall, right? It's getting very hard using these ideas to make further progress. And maybe we need to do more thinking, more breakthroughs, right? Come up with more ideas before we can go really past it. We are saturating. We are using all the compute parts, and now we are saturating. Right? So this is it, folks. I hope this. Now, one more figure that is worth mentioning is this average score of human counterparts. So what happens is that, let us say that genuinely, given a problem, you need to add so many steps to your proof. You realize that people who, human beings who score highly, right, and solve some of the harder problems, they are doing a lot of auxiliary constructions in their mind and making progress, isn't it? So how does it work? For simple problems, easy problems, the easy problems were the ones where the score, like no construction needed, just deduction only, right? And deduction only, like things that you can deduce. So this graph is interesting. It aligns the thinking of human beings with that of, I suppose, the machine, to show that this machine is beginning to think not too differently about it. I'll just read the subtext here. Among the solved problems, 2006 B6 blah 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 are the hardest problems for the Olympiad participant, right? So these were the problems in which the human beings did very bad. You look at the top box here, guys. These were the hardest problems. So for these problems, it turns out even AlphaGeometry struggled. It had to do a lot of constructions. In fact, how many constructions? Bizarrely high number of constructions, hundreds of 100 plus. Right. So it aligns. Very hard problems need more constructions, and that those problems in which the Olympiad contestants did very well. They got 5, 6, 7. Those are the scores. So if you solve it completely, I suppose you get 7 or you get 6 or whatever it is, you get partial scoring. So in those problems, AlphaGeometry also could solve it with relatively few steps, not requiring so many steps, right? Or so many constructions. If you notice that higher score it is, the lower the number of constructions or steps. Proof is shorter. Well, it was, I apologize. I shouldn't say number of constructions. I should say the length of the proof. I apologize. I use the word number of constructions, but actually it is proof length. It uses a smaller proof length. Right? So the two are aligned essentially, right? Easier problems, it solves with smaller proofs. Harder problems, it takes more longer proofs to solve. That's that. And with that, I suppose I'll stop here. Any questions on the record before? And by the way, I'm not an expert in deductive reasoning engines or any of these. So this is, I was requested to talk about this paper. And so I read this paper, understood it, and I just explained it to you guys. And not only read this paper and the blog, I also, like all of us, also watched explanations on YouTube that different people have posted. Very, very good explanations. And hopefully you found this session useful. So any questions, guys?
I had another question. I know this is my third in this session, but and obviously there may not be an answer to this, but one of the really interesting parts about this is like what happens if you're trying to do an inductive proof where you have to come up with a postulation that happens a couple of steps in the future and then kind of like work backwards from there. Do you know if like the deductive engine would be able to verify the steps like as it's going along? Because I feel like that's kind of one of the more difficult to proofs to like learn when you're in college, because like you're trying to figure out, you know, like, am I saying things that are actually making sense? Like, can I move forward as well as backwards in this proof?
See, when you do inductive proof, you say that it's true for n plus 1 because it was true for, assume that it's true for n, and now we are going to move forward with that as sort of a recursive argument. Are deductive engines able to do that? I don't know. I don't have specific expertise in this area. I would imagine that deductive engines can do that, even though they're called deductive engines. They can make the statement that let us assume it's true for this, and therefore only prove the gap true for a much larger value. I would imagine that it could in general. And deductive engines have matured actually quite a bit, and they're pretty clever as they go. It's just that they're very clever, but not creative.
Yeah, thank you.
Any other questions, folks? If none, I'm going to stop the recording. Oh, by the way, I must also say one very lovely thing about this paper, and that is becoming more of a rarity, unfortunately, these days. They have open sourced the whole code in the true spirit of research. And it's becoming so rare these days to see truly open source code in AI when everybody is shutting the door. This part I must give them kudos for.
So a general question is, this paradigm of having an LLM and then a deductive and engine at the other side can potentially be applied to lots of other domains as well, right?
Yes, so Sachin has the fact that we use a LLM and a deductive engine can be applied to a lot of other domains. I would imagine so. In fact, the next work would be to expand just beyond the very narrow Euclidean geometry problems we are seeing. For example, it's not dealing with combinatorial geometry. It's not dealing with algebraic geometry. It's not dealing with a lot of other areas that it could be dealing with, beyond geometry also, right? It could be. It's opening the door. If you remember, 2 weeks ago, we did fund search. That too was an interplay between a genetic algorithm and an LLM, right? To literally come up with better, cleverer ways. So it seems, I suppose, if there is a common thread, the common sort of a motive behind all these papers that are emerging now is that LLMs, coupled with well-established machine learning approaches like genetic algorithms, right, or evolutionary algorithms, or LLMs hybridized with deduction engines, that is where the ground for breakthroughs are, right? Let's bring back LLMs together with it. And I see it in practical. I mean, if I may put in a word from my own experience, we are working on real projects, many of them, and what we find is that LLMs are okay, but at the end of it, there's so you can do a lot of things with them, clever things with them. But when you hybridize them with, for example, a knowledge graph, or RAG is, for example, a classic example. What is it? You just put it together with semantic search, and you get retrieval augmented generation, isn't it? So more and more we are seeing that there is a huge potential for hybridizing these language models with all the other models that we have built in machine learning over the last decades, and some magic happens thereafter. Right? That's how